Take a simple sentence. I saw the man with the telescope. On the surface, this seems straightforward. You are using a telescope to observe someone. But those 7 words can describe a completely different situation. You could be looking at the man, and he is the one carrying the telescope. We usually don't even notice this confusion. Our brains use context and real-world knowledge to pick the right meaning instantly. A computer, however, only sees a flat list of words. To a machine, those words don't have a built-in owner or a clear purpose. This creates a massive hurdle for artificial intelligence. If a computer isn't certain who is holding the tool, it can't accurately follow requests or organize information. To bridge this gap, computers must map out the invisible rules tying our words together. This process of drawing a blueprint for a sentence is what experts call parsing. Think of this like taking a complex machine apart to see how the components fit together. The computer isn't just reading, it's diagramming the logic behind every word. One way to do this is by grouping words into logical chunks. By clustering related words into phrases, the computer can start to see how the sentence is built. This technique is known as constituency parsing. Take the sentence, "The cat sat on the mat." Instead of looking at 6 separate words, the computer groups them. It sees the cat as one unit doing the action, and sat on the mat as the action itself. If we go back to our telescope example, the computer uses these chunks to pick a side. If it groups the action saw together with the phrase with the telescope, the machine understands that the telescope is the tool you are using to see. But if the computer shifts the groups so the man and the telescope are in the same block, the meaning changes. Now the telescope belongs to the man, and you're just watching him. By turning a flat line of text into these nested groups, the AI finds a clear path to the meaning we intended. Sometimes, however, broad groups aren't enough. The AI might need to know exactly which specific word is modifying another. In this case, the computer looks at the sentence as a series of one-to-one connections. It identifies an anchor word and then finds the helper word that describes it. This style of mapping is called dependency parsing. For a phrase like big data, the computer points an arrow from the helper word big to the anchor word data. It establishes a clear, direct relationship. These specific links are vital when a machine needs to pull facts out of a long, messy sentence. It helps the AI identify exactly which adjective describes which noun, or which person performed which action. If grouping words gives the computer the general layout of a sentence, these direct connections provide the precise wiring that makes the whole thing work. Modern AI models, like the ones that power ChatGPT or Gemini, handle these rules even more efficiently. Rather than drawing a rigid tree or a diagram one step at a time, these models look at every word in a sentence simultaneously. They use what's called an attention mechanism to calculate which words are the most relevant to one another. It's as if the model is shining a spotlight on the connections that matter most for that specific sentence. Even though modern models work this way internally, the formal rules of parsing are still the engine behind the technology we use every day. Your voice assistant uses this logic to understand a command like set an alarm. It has to instantly separate the action you want to take from the object you want to change to get the job done. Translation apps rely on these maps to understand the role of every word. Since different languages have different grammar rules, the AI uses the blueprint of your sentence to rearrange the words so they make sense in the target language. It's also how researchers turn massive piles of text into organized databases. By identifying the subject and the action in every sentence, the AI can turn a chaotic paragraph into a set of clean, searchable facts. Every time a machine correctly translates a phrase or follows a spoken request, it successfully navigates the invisible architecture giving our language its meaning.